Okay, so be the AP Chemistry notes page, what page will this be? 31. Now at the top I have a bit of review, sorry, I mumbled. A bit of a review. For some reason it didn't come out very well in the photo. I'm talking about this section way up here, from here to here. So I'll go ahead and write that out because it's important. So let me scoot this over here. And I'm just reviewing the different types of delta H situations that we have talked about so far this year or last year. And the first one I have there is fusion. So delta H, often you'll just see it written as FUS, fusion. And that just means that it is going from solid to liquid. Now, the same value would be liquid to solid, but you'd have to reverse the sign. So it does work the other direction. The next one is the delta H of vaporization. And that's going to be liquid to gas. Or if you go the other direction, you flip the sign. And I mentioned in the notes right here, you see that I mentioned gas lab number 3 right here. That was what we calculated in gas lab 3. That was the one with the small graduated cylinder upside down in that large beaker of water. And the way we ultimately calculate it by making that graph and finding the slope and plugging it into that equation is a little bit abstract, but this is what we were solving for. I mentioned a demo here. I'll talk about that in class and actually show you, so don't worry about that right now. Then after that, we have combustion. So let me just get rid of all this stuff. So delta H, combustion. It's usually written like that. And this is going to be for a combustion reaction. And a combustion reaction is always going to be some type of fuel plus oxygen. Now, the typical reaction is that it will make CO2 and water. But there's another one that you should be aware of. Sometimes it's more of just combining the fuel and the oxygen. So an example would be and this was in the review worksheet, if you said the combustion of carbon, it'd just be carbon plus oxygen. In this case, it forms CO2. If it was magnesium and oxygen, it would form MgO. And that actually relates to a lab from, I didn't bother balancing it, but that relates to a lab that you did in first year chem, where you took a coil of magnesium, you put it in a crucible and heated it a lot with a Bunsen burner. And what you were doing is you were causing the magnesium in the crucible to react with oxygen in the air. And then you made what looked like these ashes, and the ashes were the magnesium oxide. All right, and then we need to do formation. Formation is like combustion, it's a reaction, but it's a different type of reaction. And when you do formation, delta H, normally we just write form, lazy. You must always do the elements, and they will form whatever compound. Now, the elements must be individual elements. So if it's iron, it's just regular old iron, not the ion, but neutral iron. If it's sodium, it's just regular old sodium, not Na+. The only ones you have to be careful of are the diatomics. So if it's oxygen, it would be O2, nitrogen, N2. Would be in your, this is what you would put in the reactant side to form some compound. Now regarding compounds, please be aware The term compound does not specify the type of bonding. So you could be forming something ionic or a covalent. So often there's situations. Hey, there's a squirrel running along the top of my top of my wall. Oh, it's already gone. Otherwise, I'd show you. So you know that joke where people easily distracted say, "Hey, squirrel!" That actually was a squirrel. Back to chemistry. Yeah, when you're forming a compound like this, it can be ionic or covalent. It's not specific. It just happens to be whatever it happens to be. And those are the 4 types of delta H situations we have. The first 2 are phase changes. The second 2 are actual reactions that you should be aware of. Also, when you look on a chart for the values of this stuff, it often is called the heat of something. And that's nice because it matches the symbol H, for which we have for enthalpy. But the technical right word is enthalpy. And as we discussed already, the unit is kilojoules per mole. Now, we have a couple different ways of determining delta H already. One of them was in the last lesson, where you use the bond enthalpies. And sorry, this is a little bit enthalpies. Things are going to be a little bit jumpy. I forgot to bring home my special little tablet that helps me do this. So I just have to write on the screen. Another way is what many of you are working on right now. You can find it using a lab situation, so lab data. And that's what we're going to be doing this coming up week. What I'm now going to show you is a different technique, and it's called summation. So I'll get rid of this, zoom in. And you'll see it written here, to solve for delta H of any reaction you want. It doesn't matter what type you're solving for. You can use this technique. Basically, what it is it's just final minus initial using values that are already known. So that big E is a Greek sigma, and it just means to add up all the values. And you're always going to do products minus reactants. So again, that's the same thing as saying final minus initial. And notice that it says H with a little f right here and here. That little f means formation. You must use formation values only. This technique always works with formation values. Don't use other charts. So if you use the combustion chart, it might work, you might get lucky, but it won't always work. So the safe thing to do is always use formation. But you can solve for any reaction. Sometimes when I say this, that you have to use the formation chart, people think you can only solve for formation reaction. That's not the case. You can solve for any type of reaction, whether it be combustion, some other type of reaction like decomposition or single replacement, or other reaction types that we haven't discussed yet. Another thing to note is that little circle. And the little circle is right up here. So it's in the upper right corner there and the upper right corner there. That little circle I have right here. That circle means that the values are at what's known as standard conditions. And the little circle is called not. So you would read this as H not of formation, something like that if you had to say it. And Be careful, standard conditions is not the same as STP. So let's review. STP, standard temperature and pressure, which you often see with gas problems, that's 1 atmosphere and 0 degrees Celsius. Standard conditions, and I know they sound similar, it's tricky, but it's not STP, it's different. Standard conditions is 25 degrees Celsius, which is roughly room temperature, and 1 atmosphere. So the pressure is the same, but the temperature is more like room temperature as opposed to the colder STP. So be careful here. And typically the charts are already in this situation. You don't have to worry about it. So let's take a look at the chart. It's in page 207 of the book. It's also in the big PDF I made with all those different charts. So here I have it. So page 207. And notice it says standard enthalpies of formation, 25 degrees Celsius, 1 atmosphere. Another thing to note is that if they are ions and they're dissolved in water, they will be 1 molarity. So 1 molarity, if relevant, 1 atmosphere, 25 degrees. They remind you that the unit is kilojoules per mole. So each of these values you see in the chart, this is the change in enthalpy that it takes to form these things from their elements. And so, for example, if we were to look at, let's take a look at the iron 3 hydroxide, FeOH3. And I'll go back to the other page where I can write. If I go back here and not do that silly green line I just did, move this over. If I want to write that reaction out, which you don't have to, but I just want to review this. If I want to write out the formation of FeOH3, we're going to form it, so it's got to be a product. You have to form it from its elements. So the elements would be iron, oxygen, which is diatomic, and hydrogen, which is diatomic. And notice you must use diatomics and elements. You can't use polyatomic ions. And you would balance it so that it matches. So based on the number in the chart, if we wanted to keep the delta H from the chart, if we wanted to keep that value, you have to keep this a 1 right here. That's a required 1 because this value is per mole of this stuff. Now, of course, if you want to put a number, like let's say that we decided to, for some reason, put a big 2 here. Just we had some reason to do that. That's fine. Make sure you double that value so that it matches. Typically, we don't do that. We just keep the 1, and then we let our balancing affect the other side. So in this case, to get 3 oxygens, when you balance it, you would just do 3 halves here, and to get 3 hydrogen, you would do 3 halves. Or 1.5 if you prefer decimals. And you can put states if needed. If not, you don't have to. That question comes up a lot in the class. Should we put states on our reactions? And so it comes down to 2 scenarios. If I say to put states, then put states. If I don't put states, or I don't say to put states, then decide whether they're helpful. If they're helpful, put them. If they're not helpful, don't bother complicating things. When they're helpful is usually when states are changing. If things are going from one state to another, that's usually a good time to put them because that might have meaning to the problem. Anyway, back to the chart, you see the compounds in the top, and notice some are ionic, some are covalent. And then down here are ions, which would be in solution. So notice they're all aqueous. That's how they typically exist as individual ions and not ionically bonded. Okay, so this chart will be used for the rest of this lesson. So when I'm grabbing numbers, this is where they're coming from. Back here, let's see if there's anything else that I'm missing. Oh, letter C right here. It mentions pure elements. You'll notice that pure elements aren't on the chart. The reason is because forming a pure element from itself doesn't require an enthalpy change, so its value would be 0. Sometimes you'll see them in this chart, and not this exact one, but similar charts, and you'll see the values are just a bunch of zeros. So our book just didn't bother putting them at all. All right, that covers it. Let's go to the first problem. First problem says calculate the delta H for propane, C3H8, burning in oxygen. So first thing you want to do is write your reaction, which I have. C3H8 here, O2. Always try to do the traditional CO2 and water, and then if it doesn't work, that's when you should consider the other one I mentioned. Balance it, and this is what we're looking for, is the delta H for this reaction. Now, in this case, you want to keep the fuel a 1 if possible. So try to keep this a automatic 1 right here, which, why is it, oh, there, I was too close to that arrow. Keep that a 1, that's an ugly looking 1, in front of C3H8, or whatever the fuel is. Everything else can have coefficient in front of it. I'm gonna get rid of that ugly 1. What I've done right here is I've just listed the technique I'm using. I've just said I'm using the summation technique. And by putting the little F, I'm just reminding myself to do formation reactions. The little circle means they're at standard conditions. And then you look up the values. So products on the left. So this is the value for CO2 from the chart. And I recommend you check it. This is the value for H2O. And you have to multiply them by the coefficients. So there's a 3 in front of CO2, a 4 in front of H2O. And then don't forget the negative right here, because you have to subtract the reactants. So here's the value for C3H8 from the chart, and there's an automatic 1. And then sometimes people don't even bother writing the oxygen. They go, hey, forming oxygen from oxygen takes 0 energy, so I'm not even going to write it. That's fine if you don't want to write it, but I recommend you do put it, just because this way you know that you have done it. You've kind of checked that box. And again, if this is a test, you showing me that can get you more partial credit. You're just proving that you know that that's a 0, even though it's not going to do anything mathematically. Be careful when you do the math. Students often will write out the math perfectly. So this entire thing will be absolutely perfect, yet they keep getting the wrong calculated answer because they try to do too much math at one time. So what they do is they think, oh, this is easy math. I can do it all in one step, and I'm not going to take any breaks in my calculator. And they just get lost with the negative signs and so on, or who they're adding and who they're multiplying. And so I recommend you do it in pieces. You can see I did it in 2 pieces. I did all of my products here, and I did all of my reactants here. And you should definitely do that, because you need this negative to be distributed throughout the reactants. And so if you do a solving of your products and reactants separately, then you can deal with that negative at the end, which in this case, we end up with a double negative in the math. Sig figs can get a little weird because everything is 1 past the decimal, and you can think of this problem as just a big addition and subtraction problem. I usually just keep that precision. So since the values are all 1 past the decimal, I will keep it 1 past the decimal in the answer. However, if you ever mess it up and you can argue why you chose your reason and it makes sense, I'll be fine with that as well. And then notice the units. When you get to the end of this, Each of these values on the chart was per mole because it was relative to 1 mole of that chemical. The answer is relative to this reaction. So if you just want to say kilojoules, that's fine, relative to the reaction. Or you can emphasize it and say kilojoules per mole reaction, which is actually even better. All right, next problem. Oh yeah, as usual, right now you should stop the video and try this problem for yourself, the propane burning in oxygen, see if you can do it. And then we'll try the next one. In fact, this would be best. Stop it, do the C3H8 problem, and then when you have that one figured out, try this next problem on your own before even looking at my work and see if you can sort it out. That would be even better. So moving to this one, I'm now assuming that you know how to do the other problem and have checked it. Hopefully have tried the second problem. In this case, they're just giving us a random reaction. So this isn't a combustion, it's not a formation, it's just some reaction of ammonia and dinitrogen monoxide. It's nothing of particular interest. However, they were very specific about one of the chemicals. They said 2 moles of ammonia. By them saying that, you better keep a 2 right here in front of the ammonia. So, right, one reason this is doing this, by the way, is they're making it so everyone gets the same answer. If they didn't say 2 moles of ammonia, you might balance your reaction with different size coefficients and get a different answer that is also correct. And it's hard for us to tell whether you're right or not. So that's why the 2 is there. So you write your chemicals as they stated, balance it, but keep that 2 right there. And then in this case, they said the reaction releases 879.35 kilojoules. So they're giving us the delta H of the reaction. And don't forget to add the negative because it said releases. And what they're solving or asking us to solve for is they want the H of formation. It's actually the delta H of formation for dinitrogen monoxide. In other words, it's asking, what would the chart say for this chemical right here if we were to look it up? And by the way, it's not on the chart, which makes this a good problem. So you can't look it up easily. You have to do the problem. So we're using the same technique, the summation, but this time we know what this is. They told us. Here are my products, water and nitrogen with their coefficients. Here's my reactants, NH3, and this is my unknown right here. That's what I'm looking for, is the N2O. You can call it X if you want. I just wanted to call it N2O to make it clear in the notes. Again, when you do the math, please solve the math for your products. Get a number, even though you don't see it here. Solve as much of this as you can. Distribute that negative through. And then finish off the math. You'll probably want to do this in a few steps. You can solve the products in one step, and you can solve for part of the reactants and combine everything. But do it carefully, because I remember when we do this lesson live in class, a lot of students keep calculating it wrong. Again, because they're not careful with the negatives and distributing, and they do too much math at one time. Now, in this case, your units, you can say kilojoules per mole because basically you're saying what would have been in the chart. And the chart is kilojoules per mole of whatever the chemical is. In this case, it's N2O. So you can say kilojoules per mole. You could also say kilojoules per mole N2O. and so on. I suppose you could say kilojoules per mole reaction, but you might as well just be specific. Since it is relative to one chemical, you might as well mention that chemical. All right, what's at the bottom here? Number one, do the amount of reactants in a thermoreaction make a difference on the heat produced? And yes, if you double the amount of reactants, you will theoretically double the heat. That's kind of the same thing that Hess law is saying. And two, can you use the delta H of combustion values for today's technique of summation? And so I'm emphasizing here, no, don't use the combustion values with today's technique. You can solve for the delta H of a combustion reaction or any reaction, but please only use the formation chart for this technique because the combustion one is inconsistent. All right, and homework's down there at the bottom, and that takes care of this one.